Hello, guys. My name is Harpreet Chima, and I'm joined today by my colleague Manny Singh. We both are consultants at Thorogood with experience in delivering MLOPS and data science projects for large enterprise organizations. Here's a view of what we'll be covering today. We'll quickly say a bit about Thorogood and then jump into what feature stores are, followed by a demonstration of the Databricks feature store. We'll end the session talking about where we see feature stores going in enterprise settings and thoughts we have on using them effectively. For those of you who don't know Thorogood, we are an independent, global, professional services firm specializing in business intelligence and analytics, strategies, solutions, and services with a focus on our customers. We are a global company with offices in Philadelphia, Boston, London, Bangalore, Singapore, and Sao Paulo, Brazil. All of our consultants are recruited and trained in the same way to develop a unique mix of skills, blending business understanding in the form of industry and functional experience with strong technical aptitude and a deep understanding of analytical tools and techniques. We offer a full range of data and analytics services, including strategy and roadmaps, design implementation, data analysis, and training and support. In terms of the technologies we work with, we are an independent consulting firm, meaning we don't work with one specific technology. We do, however, work and partner with many of the key players in the market in order to provide our clients with the solution that best suits their needs. And as we will see later, many of these partners are helping us to apply analytics on organizational data and productionize solutions at scale. Now let's discuss what a feature store actually is. Feature stores are properties that are used as inputs to a machine learning model. For instance, a recommendation application might use the total amount per purchase or product category as one of its many features. Generating a new feature called feature engineering takes a tremendous amount of work. The same feature must be used both for training based on historical data and for the model prediction based on the online or real-time data. This creates a significant additional engineering effort and leads to model inaccuracy when the online and offline features do not match. Furthermore, monitoring solutions must be built to track features and results and send alerts of data or model drift. A feature store is a tool for storing commonly used features, making them available for reuse. It is a central vault for storing documented, curated, and access-controlled features that can be used across many different models. A feature store transforms raw data into feature values by executing automated data pipelines, stores and manages the feature values, and retrieves data for training and scoring. The key benefit of a feature store is that it encapsulates the logic of feature transformations to automatically transform new data and serve up examples for training or scoring. If teams are continually repeating effort to code up feature transformations or copying and pasting feature engineering code from project to project, a feature store could greatly simplify the overall process and management of features. Generally, feature stores can be used to house both online and offline features. Online feature stores enable online applications to enrich feature vectors with near real-time feature data before performing inference requests. An offline feature store can store large volumes of feature data that is used to create train/test data for model development or by batch applications for model scoring. Features are made available to online and batch applications for inferencing and for creating test data models for model training. Over the last few years, we've seen explosive growth in the feature store space. Uber launched the initial concept with Michelangelo back in 2017, and since we've seen more tech companies introducing their own feature store offerings, as well as specialist feature store tool offerings. Just this last month, the first feature store summit took place. Not all of the tools offer the same capabilities in terms of integrations, online and offline serving, and supported frameworks. There are a lot of options out there, and we'll talk a bit later about how some of the most important considerations for implementing a feature store. So why are feature stores gaining traction, and why are more and more companies choosing to invest in them? And how can they help address some of the common challenges in the MLOPS lifecycle? We'll take a look at that now. The first challenge is around reusability. In many organizations, data science teams perform duplicate efforts in their feature engineering, and they have no easy way to recycle features amongst themselves. Feature stores offer a tool that provides a central repository to enable greater reusability and collaboration between teams and individuals. Many data scientists and ML engineers spend a lot of their time doing feature engineering and selection. It can be quite time intensive during the MLOps lifecycle. Feature stores offer the opportunity to save time and optimize how teams spend their time, as they don't need to start from scratch every time they start feature engineering. Features are already pre-computed and stored. As with anything in the data and AI space, data governance and tracking data lineage is always a challenge. Feature stores offer greater capabilities to monitor metadata and serve as a single source of truth for features that are being used for machine learning applications. One of the key challenges with any MLOps system is ongoing monitoring of changes in the features and the test/train data. Features can store metrics about the impact of changes on models, as well as offering the ability to identify data drift, as statistics can be compared to the feature store. Next, I'll introduce the concepts before taking us through a short demo to showcase how feature stores can be used. Before we get into the demo, let's talk a bit about the typical lifecycle of an ML model to get into production and continue serving. As you can see in this chart, raw data will flow through featureization. Those features are used for model training, service, and new inputs are served for new predictions. Now, there are two common issues that can arise. There is no reuse of the features that are created during featureization, and there could also be skew in the data sets. The inability to reuse features promotes a loss of inefficiency, where we're redoing work, and also offers the possibility of having multiple different definitions for the same feature. Online-offline skew arises when seemingly small differences in feature creation arise when developed in an offline setting versus deployed to a low latency online setting. How can we address these issues through the use of a feature store? Introducing a feature store into the mix gives the ability to continue to reuse the features from a feature registry, and the feature provider addresses the skew issue. You'll now see in the new setup after featureization, the features are registered for reuse and are served for batch model training, and the same transformations are applied before online scoring. Now let's learn more about our demo. We'll be showing a live demo of how you can use Databricks in built feature store out of the box without any additional configurations needed beyond that of typical Databricks resource. The use case is to classify the type of crystal system for batteries and could be used by manufacturers or quality assurance teams. The demo was created using the Databricks built-in feature store. Note that this library is only available on the machine learning runtime for Databricks. It is fully integrated with Databricks managed ML flow service for MLOps capabilities like tracking, logging, and serving. The feature store has both online and offline capabilities. We use the offline feature in our demo. The feature store's primary purpose is to connect your data to your model deployment. A model for machine learning has both inputs and outputs. The inputs are the features and the outputs are typically predictions. In this example, we have categorical and numerical features. As part of the feature engineering in this example, we'll show how we used one-hot encoding, string indexing, and vector assembler. And the outputs of our system is our prediction, which is the crystal type classification of a battery. Here we have our demo in Databricks. So we start by first importing the libraries. The important libraries in our demo are importing the feature store, importing the PySpark ML libraries for preprocessing and creating the actual machine learning model, and then ML flow for tracking and logging the model. First, we read in our data, and here's our data frame, and this is the raw data. As you can see, we have the numerical and categorical features, as well as our output, which is the crystal system. So first, we just want to keep our numerical features, since these are the features that we won't be doing any pre-processing on and passing through to the model. we only want to pre-process our categorical features since they are of the type string. So once we've split our features into string values and the numerical features, we can apply pre-processing. For the categorical features, we'll be applying string indexing. So what the string indexer does is it basically takes your categorical values here and it'll just index them. So for example, this first formula could be turned into a 0, and all subsequent times it's repeated in the column, it'll also be a 0. So it'll just do that with different numbers each time. And the reason we want to do this is because it allows the machine learning algorithm to actually understand the significance of the categorical features, and it also it's a better way to represent your categorical features so that you can have more accurate results. So we do that both for the formula and space group columns in this example. We also convert the column that's a string value of true and false for the has-been structure column, and we convert it into 0, 1, again for the same reason, so that the machine learning algorithm can actually understand the significance and the difference. So once we applied pre-processing, you can see this is our final data frame, and these are our pre-processed features. So we have the indexed formula, the indexed space group, and we have a 1 or 0 for true or false. So two reasons we chose these features and to pre-process them and to include them in our feature store. The first is once we've done the pre-processing once and we put them in our feature store, we don't have to do it every time we have to make new predictions. We can just go into our feature store and use this materials ID key, which is unique, to get the mapped features and put it back with the test data or the training data or the data that will be predicted on coming in. So that's one reason we don't want to do this. And the second reason that we want to keep this into our feature store is because that once you do the string indexing, it does it with the random algorithm every time. So arbitrarily, the second time you do this 4 could be a 5. So if you were to use this, if you were to do it every time, the model that you do your training on, it will be trained with a different index than what you might have when you are doing your real-time predictions. So that way, that'll lead to model inconsistency, and it'll lead to more inaccurate results. To ensure that you have your pre-processing is the same and consistent throughout, you'd want to do it once and put it into your feature store. So once you've created your feature store, your pre-processing data frame, you can create your feature store. You create your feature store by calling this module, the feature store client, and then you can create your table. In the table, you put in your features that we have up there. So we would put those 3 columns into our feature store, and we would give it the materials ID key in order to map the features back whenever we needed them. And once you've created your feature store, you can also overwrite the feature store, or you can update the feature store by using the write table command. And they both have their different use cases, so you can do either one depending on the use case you have. And once you've created your feature store, Databricks also has a UI to see your feature store. So you can go into the UI and you can click the feature store you have created, and within it, you can see the columns that you have and the data type. This is just another way that you can see the feature stores you have in your feature store and what data type they are, just to track it. And now Manny will show you how to create the modeling and the training test sets with the feature store.
Okay, so next we'll create a training set and a test set using the feature store. So the first step would be we need to specify the features that we want to retrieve from the feature store. So to do that, we'll create feature lookup objects for every feature that we want to retrieve. And we'll specify a few arguments. So the table name, that's just going to be the name of our feature table, which is the one in our case that we defined above. We'll also give the feature name, which is the name of the feature that we want to retrieve from the feature store. And then lastly is the lookup key. The lookup key is just the unique identifier that's used to retrieve the feature from the feature store. And we repeat this process for every single feature that we want to retrieve. Next, we'll create our training set and our test set. So we'll use the create training set method, and its arguments, it takes a df argument, which is a PySpark data frame that at minimum, it needs to include the lookup key, because the lookup key is used to perform a left outer join with the feature store to retrieve the features. But in addition to that, it can also include other raw features that you may not get from your feature store that came from other data sources. So it's flexible in that sense as well. Next, we'll just define the feature lookups, which we have above, and then the label, which is just what we're trying to predict in our crystal system. And for exclude columns, we'll exclude the materials ID because it will not actually be used during model training. Its only purpose was so that we could retrieve the features from the feature store. And now this is repeated for the test set. And now the load df method, this is what actually performs the left outer joins and creates our training sets. Next, just a bit more pre-processing. On our training set and our test set, the crystal system column, it still has strings in it, so we should encode that. So it will be 0, 1, or 2, so that our machine learning model can predict the integers. And now next would be, we can get to the actual model training. And before just training the model, we'll just one-hot encode the formula and space group columns just because they have many categories. So it would be helpful to create a one-hot encoding representation for them so each category can be represented. And next we'll use a vector assembler to create feature vectors, and that includes the one-hot encoded columns that we created above. And now you can see in our pipeline, we'll first one-hot encode, and then we'll create the feature vectors. That's for training and testing. And now after that, we can just fit our pipeline or train it on our training data and the test data, and then transform it. So after that, we'll have training data frame and a testing data frame that has feature vectors. Now after that, we can finally get to the model training. In this case, we're just going to use a random forest model with its default hyperparameters, and we'll train the data on the data that we got from the feature store, and we'll also test it on the same testing data that we got from the feature store. And then you can see when we evaluate the model, we see an accuracy of about 93.2%, and of course the error rate follows at 6.8%. And after this point, we can just log our random forest model using MLflow. And then if we head back into the feature store UI, this is the same screen as before. If we head down, we can see some of the features that are part of our feature store that we had, like formula and S-band structure. So if we just click on the model this time, and then we can click on the source run, you can see the random forest folder. So this is for the random forest model that we trained. And then if we expand the data folder, and then you can see the feature store folder that created for us, expand that as well. And in the feature spec.yaml file, we can see these are all the features that went up, like that went into training the model. You can see that the features that didn't come from the feature store, like formation energy, it sources training data. But if we scroll down, a feature like formula that did come from the feature store, we can see it has other attributes like the table name, and then of course the feature name, but also the lookup key that was used to retrieve it. And then also down there, the source, you can see it came from the feature store rather than the training data where all the other features came from. And that concludes the demo portion. So now we can head back and finish the presentation. So now that we've learned about how feature stores work and some of the key challenges that they can address, now let's just think about how this concept can be applied in an enterprise organization at scale. We're going to start by reviewing a few important considerations that, based on your organization and ambitions, it's going to dictate how you may use a feature store and how it may provide value to what you're doing. So firstly, how do you structure your analytical and data teams? You'd want a strategy for employing feature stores to accentuate and empower your teams without becoming burdensome and over-engineered. So we think about how you source, ingest, store, and analyze the data. And these approaches, they center on the intersection of data science, data engineering, and DevOps. So as a quick example, if you have a model with a central center of excellence or a COE, this defines a strategy and standards. And then you have local teams delivering. You may rely on the COE to define the feature store standards and set up a universal store, and then let the local team set up their local stores, all using similar naming conventions and patterns. And then next, and there's something that we can't not lose sight of, is just a feature store would be rendered useless without an effective and stable data platform. You can't build analytics and decision-making engines on top of a crumbling foundation. if you're struggling to ingest data or ensure on data quality or have volatility in your data lake and lakehouse, it's going to be difficult to truly execute and get value from the feature store. And now a final point, though likely there are many more, we need to be developing features with business objectives and needs in mind. We should define why we're generating a feature, how we define it, what it helps us answer or understand, and then how we use it in an appropriate way to influence decision making. Technology just for the sake of technology or features just for the sake of features, it misses out on business value and what we can learn about our business from a handful of features. And now with that, let's address some challenges we're seeing in expecting and implementing feature stores. Anyone that's working with data, they know that there's seemingly limitless levels of granularity and cuts of data to look at. We have different time periods, accounts, products, lines of business, and hierarchies. So when we're defining features, how do we really accommodate all these levels of granularity and lenses in a way that's accurate, scalable, and manageable? And something we may suggest is separating features by ones that are aggregable across a granularity and ones that are not. The non-aggregable features, we may look to work with the business on a few key levels to start and scale from there, expecting others to be added. And now with any complex production system, we need to be thinking about change management for feature stores, particularly in knowing the intention of a feature store is to drive adoption of downstream systems, inherently building dependencies. So to do this, we think about how our DevOps and MLOps capabilities, which help in managing solutions, and have a good understanding of how features are being used and have a close-knit community of all those working on the platform. And in a similar vein, what do we need to do to keep a feature store operating? We need to consider teams with the right engineering and data science skills to really operate the platform. And we may also look to establish various health metrics covering performance, accuracy to source, etc. And now the last one here, and maybe the most important, is driving adoption and use of the feature store. If a data scientist doesn't know how something was calculated and where it comes from, they're not going to use it. And with anything, there's a need to think about how you actually get the right folks using a feature store. And on one side of it, there's training and education. And on another is bringing your teams all along for the journey to build the store together in a squad covering technical and business angles. And another is just partnering with implementers on use cases to provide proof points of the feature store working effectively. And now, while a lot of this depends on situation and need, I hope laying out a few considerations here helps your thinking. We're also happy to speak if you'd want to talk about your specific situation or ambitions. Now, let's just wrap up in some ways we could help and where we're seeing feature stores go toward. Just potentially oversimplifying it, let's just do a rapid run through of 5 key takeaways we have in our evaluation of feature stores and what we're hearing from customers. So one, let's think about how you balance central governance, standards, and control with actual execution. This is partly going to depend on organizational structure, but it also is a big opportunity to set a foundation and pattern whilst empowering local groups to act with confidence and speed in developing features and using them to answer business questions. Second, we think about what we've learned and know about data lakes and organizing data, establishing standards, cataloging, and structuring data for consumption. Next, we apply DevOps and MLOps practices to scale a feature store, but to also integrate it in the productionization of solutions so that we have a clear path for creating new features to incorporate them in their production solutions. If we figure out an approach, one school of thought would be to build everything up front and then drive adoption from there. And another would be to just start with a handful of use cases and then use them as a way to develop the feature store and then figure standards and design out along the way. And a little bit of both probably helps. You want a reasonable plan, objectives, and approach to scaling, but you also want to act with speed and creativity to get going. And now a last one, to just realistically get buy-in and use of a feature store, it has to be explorable and consumable, which likely means maintenance of definitions, rules, etc., that can be elaborated on. Thorogood has experience helping our customers in implementation as well as strategy work, empowerment, and many others. And I'll talk a little bit about our MLOPS practice next. If we take a look at the initial workshop in more detail, it is a simple session to map out ideas and define action. We start by understanding the business drivers and possible use cases for MLOps for your organization. We bring some solutions that we have created before and then shortlist the potential candidates. Here we start delving into the candidates, mapping out the business goals and the data required to meet those goals, and with the intention of creating some initial mock-up to understand what the potential value is for the solution. And then finally, we agree the next steps to turn that initial mapping into the actual proof of value. And if this is of interest to you, then please reach out following today's session and we will be delighted to help. Thank you. That's it for the presentation.